Hi, welcome back to the ARTtech seminar. So the next speaker is an expert in AR on mobile utilizing experimental web technologies. And he's going to be talking about the lessons learned from Unity's first in-game AR advertisement. So from Unity, please welcome Matt Bengston.
Howdy. So yeah, I'm Matt. I am a software developer at Unity Technologies. I'm on our new AR ads team, where we've only been around for a couple months, but our main goal is to prototype and deliver a new type of in-game ad unit specific for passing along AR data to a web view. So our first campaign that we actually completed was for a little show called DuckTales. And this is actually the ad that we ran. So all of this runs in JavaScript. And it gives whoever's playing the game the ability to come in and walk around Scrooge's money bin, take a gander around. You walk on in, and then Scrooge pops up. He says, "What's up?" The rest of the guys pop up. And then you can just kind of explore this sort of iconic cartoon world. And all of this is running inside of a custom web view, which exposes data from ARKit to the JavaScript side, so it can actually render things in a way that appears that everything is within your same environment. So doing this, we had a couple challenges that we ran into. First off, we had a pretty tight time frame to actually prototype the tech and then to deliver the ad itself. And then another issue that we ran into is that not all the developers on the project actually were familiar with JavaScript. And if you're coming from another language, there's quite a bit of quirkiness to JavaScript that is going to take some time getting used to. And then we had some limitations that were just kind of part of our SDK. For business and historical reasons. We need to be able to deliver these things reliably and safely to upwards of 1 billion devices. So there are some limitations involved. The biggest one being that we can only deliver one file, and it has to be less than 5 megabytes, which sounds like a lot, but when you actually, these kind of things work again together to make your life hard, because since everything's in one file, you have to get all of your 2D assets, 3D assets, audio, fonts, everything all into a single HTML file. So a lot of it you have to end up base64 encoding, which then is going to blow up the size of those assets. So it ends up becoming a pretty big nightmare really fast. This can be solved by, well, our plan is to solve it in the future by having a separate bundle for assets and then a separate bundle for the actual experience, but that's further along the roadmap. We didn't really have time to do that for this particular session. And then the other issue that we had is we have no idea the performance ceilings for this. We know kind of generally what three.js's performance limitations are, but we don't know how it's going to respond when it's also being run in a web view that's also controlling ARKit, and we don't know how that's going to behave once it's running on top of a game context. So there was a lot of just unknowns that we had to kind of navigate around and see what happened. So first off, WebAR, it's pretty simple in terms of how it actually functions. You've got a web view. That web view initializes an ARKit session, and then it manages that session. And from there, each time we get data from ARKit, so every frame, we actually pass that data along to the JavaScript context for the web view so that that web view can consume that data and start moving things around how it should be. So once you get all that data, you need something to render it. We decided to go with three.js. Three.js was kind of an obvious choice for us because it's super popular and it's super lightweight. There's our second choice was Babylon, but it's just a bit too big for our needs. It's super easy to use, it's easy to write with, and it's super well documented because it's been around forever. And that's really useful when a lot of the people working on the project aren't familiar with JavaScript. It's written in a very easy-to-read way, so it's it gets away from some of the JavaScript weirdness. But unfortunately, because it is so easy to use and easy to write, it's pretty inefficient in terms of a runtime. So we had to take extra care that we weren't doing anything stupid because we already had the overhead of the runtime. So we had to make sure we were actually being smart about how we were handling things. That way, we're not adding on to that inefficiency. But all of this kind of has made it the go-to choice for doing AR with JavaScript. Like, in fact, Google has been playing around with WebAR as well, and they've also created some of the tooling that we've used here. Because basically what you need to actually do this is you need to have some sort of camera that is absorbing all of those view matrices, camera pose data, and all that, and applying it to a three.js camera. That's pretty much the basis of what you need to actually start walking around 3D objects with JavaScript. And so Google has actually made a helper library that solves this problem for you. So it's just three.ar.js, and it serves as an extension to three.js, and it provides you with a perspective camera that already consumes all of that AR data, already applies the view matrices, already applies the pose data, and along with some controls. So it makes it super easy to actually get up and running. You just initialize that and call it a day. It already will start working the second it starts getting data from ARKit. And then it also has a hit testing method, which is really useful because then you don't have to worry about creating that bridge between native and JavaScript. So once we had that figured out, we needed to figure out a good dev environment, especially because not everybody was familiar with JavaScript. I think I was the only person on that project that has actually used JavaScript regularly for a while. So we wanted to go with something like a Node.js-based environment, something that's like modular, because it's a little bit easier to come to grips with, as opposed to normal kind of like Wild West browser JavaScript. And so our requirements for this is that it had to be easy to understand for the people that aren't really familiar with JavaScript. If there's a problem, anybody should be able to see exactly what is the problem really easily. It needed to be extensible because we're kind of playing around with stuff that hasn't really been played around with. So we needed to be able to create plugins for this very easily and in a very short time frame, because for the entire project, we did not have a very long time frame. And then we needed to be able to have a quick iteration loop. So kind of like when you're building something in Unity, for example, you can literally make one change, hit the play button, and then play it and see exactly what that change has done. So we wanted something similar, but just with three.js. So to do that, we basically use this bundler called Rollup.js, which solved all of these problems for us. There's a bunch out there. There's Webpack, there's Browserify. This one was the one that, for us, made the most sense because it was really easy and transparent in terms of its configuration. A lot of times with JavaScript, it'll be, especially with JavaScript kind of like libraries, you get lost in these massive question mark like options and parameters that are maybe not very well documented, and you kind of have to play a guessing game to figure out what's actually making anything happen. This one, it's also really straightforward to extend. So like we wound up doing 3 different plugins for this, and we were able to implement each one of them in less than a day, which is really nice when your project is depending on this. And it's got really efficient tree shaking, which is just a goofy way of saying dead code elimination. So it was originally created by somebody who was really into the new ES6 modules implementation, which is basically it only brings in the code that's actually being used. It analyzes your code as you're writing it, and only the things that are actually used get put into the final bundle, which when we were having to try and deal with these kind of size restraints was really important for us because it allowed us to not include parts of three.js that we weren't even actually using or needed. And the best part was there was already a dev server extension readily available, so we didn't have to worry about writing that, and it builds really fast. So we could just make a change, refresh our page, refresh our little like WebAR browser, and then we could see the latest and greatest immediately. So once we had that, we started to actually implement the kind of like portal and everything, as well as our artist, Johanni, started working on the actual environment creation, which is kind of an exercise in how much can we fake this and make it still look really good. So he actually, when we were doing some testing on three.js performance, one thing that we noticed was a major performance killer immediately was lights. So we made the conscious decision to just go with completely unlit everything. And it kind of worked because it's a 2D environment where there's lots of 2D details. So our artist actually went through, and all of these details are baked into the geometry. And then he's got a little, because we're also having to worry about these asset sizes, our texture sheet is just a little tiny color palette. And then the things that absolutely have to have some sort of pattern on it, we have those, but as small as possible. But the vast majority of this is actually just a little tiny color palette up there. It's that in the top left corner. So all of the, he was sitting there just shifting everything around and then shifting the UVs so that they would fit on there to whatever color they actually needed. And you can actually, you might imagine this might make a little bit of a mess on the UV map, and you'd be absolutely right. It's a little bit sketchy, but it worked really well for us, and it was really good because it gave us the freedom to start kind of like not having to worry about asset sizes and playing around with like lighting configs or anything like that. All we had to worry about is getting that model into the runtime, and we don't have to worry about it. We don't have to worry about figuring out how to compress these massive images. So for our actual like asset pipeline of getting these things into JavaScript, we went a little bit overboard with pre-processing. We could probably clean this up in like our next iterations, but it worked for now. But we basically, as I said, everything has to be inlined into a single file, which becomes a little bit tedious and becomes a little bit of a pain. So we wound up writing a couple scripts that did this for us. So we have one for audio that we've got all of the audio goes in a folder, you run the script, it'll go through, find everything, base64 encode it, and toss it into a JavaScript module, so you can just import it directly and use it. Same for, we have these big sprite sheets. Each one of those little characters that was inside of the vault, they are their own little sprite sheet, and they're treated as a 2D sprite. And so each one of those also had their own thing because those were exported from formerly Flash, now Adobe Animate, RIP Flash. And those basically had the giant sprite sheet and then a JSON dictionary that said where each frame was. So we went through, we have a script that went through there and then compressed everything as much as we possibly could and translated those into a JavaScript object that we could use directly in the actual code itself. Another thing that we also did was for our 3D stuff, we wound up using the GLTF file format, which it's written by the same guys that did OpenGL and WebGL. So it's super, super, super good. Like, I highly recommend it. It's written in a way that it makes it super efficient in terms of runtime loading and actually storing of the data. So we wound up using that, and then our artists would give us FBX files, and then we would pipe that through our conversion scripts, which would then spit out a GLTF file. Now, some of the newer versions of like Modo, for example, have GLTF exports available. So this, if we have done this like a couple months later, we wouldn't have had to worry about this, but it worked for us at the time. And then from there, we created a Rollup.js plugin for resolving these GLTF assets. So it kind of made it when you're actually writing the gameplay programming, you didn't have to worry about where that asset was or anything. You just say, hey, I want this file. I just want this 3D file. And then Rollup will actually inline all of that for you when it builds the bundle. And what you end up with at runtime is just a nice little GLTF JSON dictionary that you can toss into the three.js loader, and it works automatically. So all of this worked really, really good. But we ran into a little bit of an issue, which was, you may have remembered I said we have like a 5 megabyte hard limit, and we quickly went past that. But we found something that came to our rescue, which is something called Draco compression, which is written by Google, and it immediately dropped our file size by like 65%. It's great. So this is just like one little option on all GLTF encoders, and it just affects the actual buffer that the geometry is stored in. So from a development point of view, we didn't even have to worry about the fact that we were using a different type of compression. It just sort of magically worked, which was really, really good, and it made us not have to worry about stuff like that and just focus on actually getting this project done. And because of this, we ended up having this nice little kind of like bundle of mostly 2D assets, high-res 2D assets. So like we've got our start card and our end card, which are all very high resolution, like straight from the designers, and they have to be as high resolution as possible. And we've got our sprite sheets, which are the very large portion of the bottom left. That's all the 2D sprite sheets. And then the top right is like the high-res assets for like marketing purposes. And then 3D wound up not really taking up that much at all. We got quite a large chunk of just runtime dependencies. So that's like three.js, three.ar.js, the Draco compressions, like runtime libraries. So we wound up getting a pretty good even distribution of space, which is really nice because just by enabling that one option, we were saved. So for gameplay, there wasn't really too much super special about what we did here. There's things that we've noticed, and there's things that we could do better on in the future. For example, one thing we noticed is that portals take up lots of space. If you're on a bus, you don't really have the luxury of walking 5 meters to walk inside of a virtual portal, unless you got really good balance and you can do that. But not everybody's going to be able to do that. So we wound up doing like a tap to enter thing, so that if somebody was on a bus and a train, something like that, they could just tap exactly where they wanted to go and then call it a day. And it would teleport them into the portal, and they could then look around and do whatever they needed to do. And then we also, because we faked so much, we didn't want it to be super apparent how much we faked. So we wound up making this boundary system so that we could kind of control where the actual player could go. So if you actually tried to go out of that boundary area, we would then move the portal, the entire like geometry with you, which is maybe not the best way to go about it, but at least for us, it made sense because as we move the world with you, you still have the same amount of space between wherever you are and the exit of the portal. Whereas if we just, did some other approach where we didn't really move it and we just somehow kind of like stopped you from going any further, like stopped the camera from moving, then you would have a huge walk back if you actually wanted to leave the portal, which we thought didn't really make any sense. And then another thing we probably could have done better is placing entities manually with three.js was an absolute pain. We probably should have just had our artists create empty nodes throughout where where all the entities needed to go. And that way, whenever we were initializing them, we could just grab that like reference point and initialize it there. Because we lost a fair bit of time just like manually moving things around, and there was really no need for it. But we've got that lesson for next time at least. And from the entire project, like our main learnings are that you can already do really amazing things with WebAR. It's not really a finalized spec yet, but even with it in its unfinalized form, you can do a surprising amount with it. Like we were able to make a portal with it with no problems. You can do plane detection. You can do everything that normal AR can do, and you can do it with JavaScript, which I think is super powerful. You can, once it actually lands in browsers, like anybody who has an enabled browser can have a full, decent, like solid, well-performing experience just on the web. And I think that's going to do wonders for AR. Another thing we've learned is that GLTF and like Draco compression is a majorly winning combo when it comes to 3D, especially for anything that is doing any sort of streaming. And I would, if you're doing anything like that, I would highly recommend taking a look at it because all of the tooling around it is already so good, and it's actually a very, very, very good format to work with and to use. And if you use Draco compression, then you don't have to worry about size constraints. Like it's definitely a winning combo. And then another one is that making sure your development environment is solid makes a huge difference. I don't think we would have been able to do the project in the time that we did it if we didn't spend the time at the beginning to actually make a good development environment, especially considering that not everybody was familiar with the language. because otherwise you're going to spend all this time just kind of onboarding and getting used to how things work. So if you spend that time in the beginning making sure that everything works so that you don't have to actually worry about it after the fact, then you've got all this time now afterwards of just focusing on what you need to do as opposed to trying to fight with your development process. And it makes a huge difference, and it can be overlooked, but definitely like keep that in mind. Like make sure everything is easy to use for yourself, and it'll save you a lot of heartache in the future. And yeah, that's it, unless there's any questions. Uh-oh.
Does it work? Okay.
Oh, there we go.
Thank you for a great talk. AR ads are definitely a novel area of interest. So you mentioned before that you had developed a way for users to experience the DuckTales ad without actually having to physically move in the environment, but only just by tapping they could enter the portal.
Yeah.
Do you have like data points or estimates of like how many, like what's the percentage of users who do move in the AR environment, and how many of them would just experience the ad just by like without moving, just from sitting?
So we do have some analytics for this. I can't remember them off the top of my head, but it was actually a surprising amount of people did use the tap to enter. I think it was like 25% or so, maybe 30. But I think we could have maybe done a better job at advertising if that was something that you could do, and then more people might have used it. But the people that did actually use it wound up staying in the experience for longer. So, and we had like analytics for when people enter, so we could see that like people that were maybe not entering, there was definitely people that did tap spent longer in it than people who didn't really bother.
Gotcha.
Yeah.
All right. Thank you so much.
Yep.
Okay, we don't have more questions. Thank you, Matt.
Thank you.